These are the answers to the AP Chemistry packet that is entitled Unit 5, Summative Assessment Practice. On this slide, you can see Unit 5 at a glance. Unit 5 is entitled Kinetics. In this video, I will present problems that cover almost all of the topics in Unit 5. This video should help you to prepare for the Unit 5 Summative Assessment. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Okay, let's get started. The instructions that you see on this slide are the same instructions that you will see on the AP Chemistry free response section. Show your work for each question in the space provided. Examples and equations may be included in your responses where appropriate. For calculations, clearly show the method used and the steps involved in arriving at your answers. You must show your work to receive credit for your answer. Pay attention to significant figures. Even though this packet is designed to be a review of the chemistry in Unit 5, Kinetics, there are certain parts of questions in this packet that are intended to be a review of chemistry from earlier units that you have already studied. For example, parts A and B of question 1 come from Unit 4, which is entitled Chemical Reactions. Question 1 says the following: the reaction between solid lithium and liquid water is represented by the equation shown above. Part A: a student makes the claim that the reaction represented by the equation shown above is classified as an oxidation reduction or redox reaction. Do you agree or disagree with the student's claim? Well, based on the fact that there are certain oxidation numbers that are changing in this reaction, I will say yes, I agree with the student's claim. But now it says to justify your answer by assigning oxidation numbers to each element on both sides of the equation. So here is a brief review of some of the rules for assigning oxidation numbers. This rule says that if an atom is in its elemental form, the oxidation number is 0. So we see on the left side of the equation solid lithium, and on the right side of the equation we see gaseous hydrogen. Those substances in their elemental form have oxidation numbers of 0. This rule says that the oxidation number of a metal in group 1 is +1 in all compounds. So since lithium is a member of group 1, in the compound lithium hydroxide, on the right side of the equation, LiOH, lithium carries an oxidation number of +1. This rule says that the oxidation number of hydrogen is usually +1 when hydrogen is bonded to nonmetals. So we see H2O on the left, and we see LiOH on the right. Hydrogen carries an oxidation number of +1 in both of those compounds. And this rule says that the oxidation number of oxygen is usually -2 in most ionic and molecular compounds. So for water and lithium hydroxide, oxygen carries an oxidation number of -2. So to summarize the changes in oxidation number, lithium is changing from 0 to +1, so lithium is being oxidized, and hydrogen is changing from +1 to an oxidation state of 0 in gaseous hydrogen, so hydrogen is being reduced from +1 to 0. All right, moving on to part B of this question, it says write the balanced net ionic equation for the reaction represented by the equation shown above. You do not need to include the symbols for phases of matter. When you are writing a net ionic equation, an important question to ask is, do I split up the formula into separate ions or leave it unchanged? Well, if you see a pure substance that is a gas, a liquid, a solid, or if you see a substance that you know is covalent or molecular, that exists in the form of molecules, then you would leave it unchanged. So on the left side of the equation, we see solid lithium And that's an element, so we're not really going to split up an element anyway, but that would definitely be something that you would not split up. We see liquid water, and that is a covalent or molecular substance that would exist in the form of molecules, so we're not going to split that up. And on the other side of the equation, we see hydrogen gas. And again, that's an element. We're not going to split that up into ions. Now, if you, on the other hand, see an aqueous ionic compound or an aqueous strong acid, then you would split it up into separate ions. And since lithium hydroxide on the right is an aqueous ionic compound, then we would split that up into the lithium ions and the hydroxide ions. So on the left side of the equation, we just simply write the formulas exactly as they are. And on the right side of the equation, we're going to split up the 2 moles of lithium hydroxide into 2 moles of aqueous lithium ions. Don't forget to put the charges on your ions. And then 2 moles of aqueous hydroxide ions. Hydrogen gas remains exactly as is. Now, normally we would cross off the spectator ions that appear on both sides of the equation, but in this case, there are no spectator ions to eliminate. Everything on the left is going to remain exactly as is, and the only thing we really did on the right side of the equation was simply show that the lithium hydroxide was fully dissociated into separate ions. So that is the answer to part B. All right, moving on to part C, now we get a question that relates to Unit 5, kinetics. Part C says 2 different trials for this reaction were performed under different conditions according to the information shown above. So as you can see in the table, in trials 1 and 2, it's the same mass of lithium, the same form of solid lithium, the same volume of liquid water, but trial 2 carries out the reaction at a higher temperature. In which trial should the reaction occur at the faster initial rate? Justify your choice by describing how the collisions between reactant particles are affected by the specific change that was made in the experimental conditions. So simply saying that trial 2 should be faster because the temperature is higher would not be enough, because you have to talk about what's happening to the particles. In an earlier video, when I was exploring the variables that affect reaction rate, things like temperature, surface area, concentration, what I had said about temperature was that at the higher temperature, the reactant particles collide with each other more frequently and with more force. So that's the language I'm going to use here in part C, that the reaction in trial 2 should occur at a faster initial rate because the reaction occurs at a higher temperature. The reactant particles in trial 2 will collide with each other more frequently and with more force, and this explains why the initial reaction rate in trial 2 is faster than it is in trial 1. Now, before I move on to question 2, some of you might be asking the question about activation energy at this point. In other words, do I have to mention that at a higher temperature, a greater fraction of the collisions will have enough energy to overcome the activation energy? In this particular question, there was no mention of activation energy specifically, so I didn't include that in my explanation. But in question 8 of this packet, you will see a Maxwell-Boltzmann distribution curve for the collision energies, and then I will talk about what happens when you increase the temperature and a greater fraction of the collisions will have the required activation energy. All right, let's move on to question 2. Here we have a question that involves stoichiometry and the coefficients in the balanced chemical equation. It says gaseous ammonia, NH3, can be synthesized from nitrogen and hydrogen according to the equation shown above. At a certain point in time during the reaction, the rate of formation of NH3 was equal to 0.018 moles per liter per second. Calculate the rate of disappearance of hydrogen at that same point in time. Include units in your answer. So moles per liter per second, those are the units of rate. And so I'm going to write that number down, 0.018. It's moles of ammonia, NH3, per liter per second. I'd like to get rid of ammonia and convert into hydrogen. So I'll put moles of ammonia on the bottom and then put moles of hydrogen on the top. So the coefficients would be 3 moles of hydrogen are consumed for every 2 moles of ammonia that are produced. Now when I do this math, I will have units for hydrogen's disappearance, and it would be moles per liter per second. So when I do this math of 0.018 times 3 divided by 2, I get 0.027, and you can write molarity because that is moles per liter per second. So the units are molarity per second, and that number is for the rate of disappearance of hydrogen at that same point in time. Now let's move on to question 3 in the packet. So in question 3, it says the equation for the reaction between HgCl2, that's mercury chloride, and C2O42-, that's an ion known as oxalate, that equation for the reaction is shown above, and the initial rate of formation of chloride at constant temperature was measured in different trials with various initial concentrations of the reactants as shown in the following table. Part A. Determine the order of the reaction with respect to mercury chloride. Justify your answer. So what I'm looking for is a set of experiments in which they changed the initial concentration of HgCl2 while keeping constant the initial concentration of the other reactant. So I'm going to compare trial 3 with trial 2 because in that situation they doubled the initial concentration of HgCl2 while keeping constant the concentration of the other reactant. Let's see what happened to the initial rate of formation of chloride. Well, it looks like because of that change, the rate was doubled, so therefore we can conclude that this particular reaction is first order with respect to HgCl2. So here's what I said. Compare the data for trial 3 with the data for trial 2. The initial concentration of HgCl2 is doubled, while the initial concentration of C2O42- remains constant. As a result of this change, the initial rate of formation for chloride is doubled. Therefore, we can say that this reaction is first order with respect to HgCl2. Now, moving on to part B, we're going to use that same process. Determine the order of the reaction with respect to the oxalate ion, C2O42-. So I'm looking for trials in which they kept constant the initial concentration of HgCl2, but they changed the initial concentration of the oxalate ion. So I will compare trial 1 with trial 2. So HgCl2's initial concentration was constant. They doubled the initial concentration of the oxalate ion, and let's see what happened to the rate as a result. Well, it increased, but this time by a factor of 4. So now we can say that this reaction is second order with respect to C2O42-. So here's what I said. Compare the data for trial 1 with the data for trial 2. The initial concentration of C2O42- is doubled, while the initial concentration of HgCl2 remains constant. As a result of this change, the initial rate of formation of chloride is quadrupled. Therefore, we can say that this reaction is second order with respect to C2O42-. And so now that we know from our answers to part A and B what the order of the reaction is with respect to each reactant, we can write the rate law. So in part C, it says write the rate law for the reaction. So we know that this is first order with respect to HgCl2 and second order with respect to C2O42-. So those are the exponents that we use in the rate law. So rate equals K, the rate constant, times the concentration of each reactant raised to its appropriate power, the order. What I like about this situation in this question is that notice that the order with respect to each reactant does not match the coefficient of that reactant in the overall balanced chemical equation. So it kind of reinforces the idea that you get your order from the experimental data and the analysis of that data. You do not get the order from the coefficient in the overall balanced chemical equation. All right, now in part D, now that we have a rate law, calculate the value of the rate constant K for the reaction. Include units in your answer. So because they carried out all of these trials at the same temperature, that means that I should get the same value for the rate constant K no matter which trial I choose. Now I can't use trial 4 because I don't have enough information, but I can use the data for trial 1 or trial 2 or trial 3, and I should get the same value for the rate constant K. So I'm going to start with trial 1. What I have in terms of my data is I have the initial rate, which is 5.44 times 10 to the negative 5, and the units are molarity per minute. And then I have the rate constant K, which I don't know yet. I have the initial concentration of HgCl2, which is 0.0850 moles per liter. And I have the initial concentration of C2O42-, which is 0.200 moles per liter. But that number is squared because it's second order with respect to that chemical. So when I do this math and I solve for K, what I get on my calculator when I do the math is 0.0160 for the numerical value of the rate constant. But it says include units in your answer. So for the units, I have molarity per minute on top, and I have molarity cubed on the bottom. So when I resolve the units, it's going to be molarity to the negative 2 power, and then minutes to the negative 1 power. So that is my numerical answer with the proper units. Now I'm going to go ahead and show you the calculations for trial 2 and for trial 3, just to prove that you would get the same answer no matter which trial you chose. So here's the data for trial 2. So I plug in those numbers. Again, I'm using the rate law that says it's first order with respect to HgCl2, second order with respect to C2O42-, so don't forget to square the concentration of the oxalate ion. And when I do the math, again, I get 0.0160, and my units are molarity to the negative 2 power, minutes to the negative 1. So that was the data for trial 2, and here is the data for trial 3. And you can see, hopefully, that no matter which trial you had chosen, you would have gotten the same numerical answer, and again, make sure that the units are correct. Well, now that we know the value of the rate constant, we can go ahead and figure out the value for the initial concentration of oxalate in trial 4. So now what I'm going to do is take the data from trial 4 and plug it into the rate law so I can solve for the initial concentration of C2O42-. So my initial rate is 3.01 times 10 to the negative 4 molarity per minute. My rate constant from part D is 0.0160, and the units are molarity to the negative 2 power, minutes to the negative 1. My initial concentration of HgCl2 is 0.0675 molarity, or moles per liter. And then since I don't know the initial concentration of the C2O42- ion, I've just written that, but don't forget it should be squared because it's second order with respect to that chemical in the rate law. So here is me doing the math to solve for the concentration squared. So when I do this math on my calculator, I get 0.2787. That's not my final answer because that still is the quantity, the concentration squared. So now I have to take the square root of that number to get my final answer. So my final answer is 0.528 moles per liter. Well, hopefully that calculation makes sense. Let's move on to question 4. In question 4, it says, a kinetics experiment was done to study the decomposition of nitrogen dioxide, NO2. The concentration of NO2 in a rigid reaction vessel is monitored over time as it decomposes at 500 Kelvin. The data from the experiment is shown in the table below. Part A, fill in the missing data in the table below. Round off all of the calculated values in the table to 3 significant figures. So before I pick up my calculator, let me just give you some context for the purpose of doing these calculations in Part A. We're trying to determine the order with respect to NO2. So we have a data table that shows that concentration of NO2 is decreasing over time. One of these 3 columns, either concentration or natural log of concentration or the reciprocal of concentration, one of these 3 columns should show a linear relationship. So for example, if concentration of NO2 versus time represents a linear relationship, then that would be 0 order with respect to NO2. But if instead the natural log of concentration versus time indicates a linear relationship, then it would be first order with respect to NO2. And if the reciprocal of the concentration versus time indicates a linear relationship, it would be second order with respect to NO2. Now, as far as concentration versus time, watch what happens when I take the difference between these concentration values. Again, every 20 seconds, the concentration goes down, but take a look. So in the first 20 seconds, the concentration decreases by 0.0324. In the next 20-second interval, it decreases, but by a different amount. And then the next 20 seconds, it's decreasing. But again, these are not showing a linear relationship because it's not decreasing by the same amount every 20 seconds. So now I'm going to pick up my calculator and do the natural log of 0.1, which is negative 2.30. Again, I'm rounding off my calculated values to 3 significant figures. I take the natural log of 0.0676, and I get negative 2.69. And then I'll keep going, taking the natural log of the concentration at 40 seconds, at 60 seconds, and 80 seconds. So I have those values now filled in for that column, taking the natural log of the concentration. Now for that final column, it's going to be 1 divided by the concentration. So 1 divided by 0.1 is 10.0. Again, 3 significant figures. 1 divided by 0.0676, 14.8. 1 divided by 0.0510, 19.6, and so forth. So I now have the data table filled in, but I'm still thinking for, is there a linear relationship between either the natural log of concentration over time or the reciprocal of the concentration over time? So I'm going to subtract the 2 values and see if I can find a regular interval or a pattern. So natural log of concentration is decreasing, but hopefully you can see it's not decreasing by the same interval every 20 seconds. But watch what happens when I look at the change in the value for the reciprocal of concentration of NO2. So it's increasing by 4.8, increasing by 4.8, 4.8. So there it is. So that tells me that the graph of 1 over the concentration of NO2 versus time would in fact give me a straight line. So now I know that because that is going to give me a linear relationship, it is going to be second order with respect to NO2. So my answer to part A was just filling in the data, but now I'm analyzing that data. Part B, what is the order of the reaction with respect to NO2? The reaction is second order with respect to NO2 because the plot of 1 over NO2 versus time is linear. So my rate law would be rate equals K times the concentration of NO2 raised to the second power because it's second order with respect to NO2. Now let's take a look at part D of this question. It says the initial reaction rate is determined to be 0.0012 moles per liter per second. Calculate the value of the rate constant K for the decomposition of NO2 at 500 kelvins. Include units in your answer. So we have a rate law. We have an initial concentration of NO2 at time 0. Let's plug in everything we know from this particular question into the rate law. So the rate would be 0.0012 moles per liter per second. The rate constant is unknown at this point, and the initial concentration of NO2 is 0.100 moles per liter, and that quantity is squared because it's second order with respect to NO2. So I'm going to go ahead and just solve for K. Mathematically, it's going to be 0.0012 divided by 0.1 squared. And so when I do that math, I get 0.12 on my calculator. As far as the units of the rate constant, I have molarity per second on top and molarity squared on the bottom. So when I resolve those units, I get molarity to the -1, seconds to the -1. So there is my numerical value of the rate constant, 0.12, and my units are molarity to the -1, seconds to the -1. All right, in part E of this question, it says calculate the time required in seconds for the concentration of NO2 to change from 0.100 molar to 0.0500 molar in this experiment. Now, you can look at this math and you can say that 0.05 is exactly half of 0.1. However, be careful. You can only use the half-life equation on the AP equations and constant sheet if you have first-order kinetics, and we do not have a first-order rate law. Even though this looks like it might be a half-life question, you have to use the second-order equation to do the math in this problem. So again, be careful that you don't just automatically pick up the half-life equation, because that would be the wrong equation to use. So I've got my rate constant from part D, which is 0.12 inverse molarity, inverse seconds. There's my second order equation, and the initial concentration is 0.100 moles per liter. The final concentration at time t is 0.0500 moles per liter. I've got my rate constant in there. The only thing I don't know is the time. So now I'm going to do the math. So 1 divided by 0.05 is 20. 1 divided by 0.1 is 10. And again, I'm just going to do that particular calculation to solve for t. And when I do this, I get a value of time in seconds of 83.3 seconds. Now, this might cause a problem for some of you. If you look closely at the data in the table, it might seem that 83.3 seconds is actually incorrect or doesn't quite make sense. Take a look. We're trying to figure out how much time it takes for the concentration of NO2 to drop to a value of 0.05 moles per liter. So according to the data in the table, it would seem that the time required for the concentration of NO2 to reach a value of 0.05 moles per liter should be somewhere between 40 and 60 seconds, and yet we just got an answer of 83.3 seconds. So this might be a concern for you. Let's take a look more closely at why this seems like it didn't quite work out properly. So what you see on this particular slide are three graphs. We have concentration versus time, natural log of concentration versus time, and 1 over the concentration versus time. And as you've learned in this unit, if concentration versus time is linear, it would be 0 order with respect to A. If natural log of concentration versus time is linear, it would be first order with respect to A. And if 1 over the concentration versus time is linear, it'd be second order. But this is for a generic reaction in which 1 mole of A goes to 1 mole of B. Now, the rate constant, K, should be the absolute value of the slope of that line. But again, we're assuming that we have 1 mole of A going to 1 mole of B. So the rate of formation of product is the same as the rate of disappearance of reactant. What if the reaction looks like this, where 2 moles of A are changing into 1 mole of A subscript 2? Well, now the rate of reaction, which would be the rate of formation of product, is not the same as the rate of disappearance of the reactant. So as you can see, based on the stoichiometry in this example, the rate of disappearance of the reactant A would actually be twice as much as the rate of formation of the product. And so if you're plotting the change in concentration of the reactant over time, because the rate of disappearance of A, because of that coefficient of 2 in this particular equation, the rate of disappearance of A is actually twice as much as the rate of the reaction. So the slope of this line would actually be 2K and not K. Now, if that's a little confusing, let me see if I can process with you here. Here was the data that we've already looked at earlier in part A. The value for the reciprocal of the concentration was changing from 10 to 14.8 to 19.6, etc. It was changing by 4.8 units every 20 seconds. So the slope of that line would actually be not 0.12 like we looked at earlier in terms of the rate constant, but twice that value. So again, if you have a coefficient of 2 in your reactant, then the rate of disappearance of that reactant would be twice as much as the rate of the reaction. So if you're wondering, oh, do I have to use the slope of the line? Well, it turns out that I would accept an answer either way, depending on which value of the rate constant that you used. So let me go ahead and show you what I'm talking about. So if we go back and do that calculation, but now instead of the rate constant being 0.12, what if it's 0.24? So I'm going to go ahead and run those numbers with a different value for K. Now when I do this math and I solve for the time, instead of getting around 80 seconds, I get 41.7 seconds, and that would be consistent with the data in the table. So to summarize, in the answer to part E, if you had used a rate constant of 0.12, then you would have gotten a time of 83.3 seconds. If you had used a rate constant of 0.24, then you would have gotten a time of 41.7 seconds. So depending on which value of K you used, either of those calculated values for part E would be accepted. So I apologize if that was a little confusing to you, but I just wanted to make sure that you understand that the situation here was because we had a coefficient of 2 in the disappearance of the reactant. It was twice as much as the formation of the product. That's why the slope of the line would actually be 2K as opposed to K. All right, so now I'm going to move on to part F of this question, and we're going to have the same situation in part F, where depending on which value of K you use, you're going to get two different answers, and I'll show you both of those. All right, so here is part F. Calculate the concentration of NO2 in moles per liter that should be present in the reaction vessel in this experiment when the reaction time is equal to 100 seconds. So if I use a value of K of 0.24, and I use my second order equation, I know that the initial concentration of A, in this case the NO2, the initial concentration was 0.100 moles per liter. That came from the table. I know that the time is 100 seconds. I'm going to solve for the concentration at 100 seconds. And when I do this math, I end up with a value of 0.0294 moles per liter. And that value does make sense to me because after 100 seconds, the concentration of NO2 should be a value less than 0.0342. In other words, it would decrease after 80 seconds. So at 100 seconds, it should be less than that. So that number does seem reasonable to me. But if you had used a value for the rate constant K of 0.12, you would have gotten a different answer. Let me show you. So had you used 0.12 for your rate constant, and you're solving for the concentration at time t, at 100 seconds in this case, our time is 100 seconds, then you would have gotten a value of 0.0455 moles per liter. So just like I showed you in part E, in part F, there were actually two different possible answers to part F. Either of these would have been acceptable depending on which value of K you used. All right, let's take a look at part G of this question. The following two-step mechanism has been proposed for the decomposition of NO2. So we have the step 1 and step 2. We're going to add them together. And if there's anything I can cross off on both sides of the equation, like an intermediate, I would take care of that. So I see molecular NO2 is decomposing to NO and atomic oxygen, but then the atomic oxygen is actually consumed as a reactant in step 2. So I cross that off. And then there is my overall balanced chemical equation with 2 moles of NO2 on the left, 2 moles of NO on the right, and 1 mole of O2. Now, part H of this question is focusing on the mechanism and is this consistent with the experimentally determined rate law that we wrote in part C. Remember, it's a second order rate law. What I focus on in a mechanism is the rate determining step. So in this case, step 1 is the slow rate determining step. And here's a problem. There's only 1 molecule of NO2 as a reactant in this slow rate determining step. So therefore, this is not going to be consistent with the experimentally determined rate law, because if I focus on step 1, there's only 1 molecule of NO2. So the answer is no. The rate law derived from this proposed mechanism is not consistent with the experimentally determined rate law that was written in part C. In this proposed mechanism, step 1 is identified as the slow rate determining step. And the rate law derived from step 1, because there's only 1 molecule of NO2 featured as a reactant, would be first order with respect to NO2. And this is not consistent with the second order rate law that was written in part C. Let's move on to question 5. Carbon-11 is an isotope of carbon that undergoes a nuclear decay process in which it is converted into boron-11. The half-life for this decay process is equal to 20.3 minutes. Part A. Calculate the value of the rate constant, K, for the nuclear decay of carbon-11. Include units in your answer. Remember that radioactive decay processes provide an important illustration of first-order kinetics. In nuclear decay, the composition of the atomic nucleus changes. In a chemical reaction, chemical bonds are broken and/or formed, but since the half-life remains constant during nuclear decay, it is classified as a first-order process. So the equation that we're going to use to calculate the rate constant, since we already know the half-life is equal to 20.3 minutes, is this half-life equation, which says half-life is equal to 0.693 divided by the rate constant. Let's rearrange that equation so that the rate constant is equal to 0.693 divided by the half-life. So we'll take 0.693, divide by 20.3 minutes, and we get our numerical answer, which is 0.0341. And the units of a first-order rate constant are always inverse time. In this case, inverse minutes. So the units are minutes to the -1, or 1 over minutes. Now that we know the rate constant, we can process the calculations in parts B and C of this question. In part B, it says a pure sample of carbon-11 with a mass of 275 milligrams undergoes nuclear decay. Calculate the mass in milligrams of carbon-11 present in this sample after 75.0 minutes. So we're still going to use the first order equations, in this case not the half-life equation, but rather the equation that involves natural log. The amount present at time t is what we're trying to find. So the initial amount is 275 milligrams, and even though normally that would be molarity or moles per liter, because of this nuclear decay process, we can just go ahead and process the amount in grams or milligrams. So 275 milligrams is the initial amount. The rate constant is 0.0341 inverse minutes, which we've already calculated in part A. The total time is 75.0 minutes, and so we're solving for the amount present at time t. So now it's just a matter of doing the math and using your calculator for this. And right at the end, we get that E raised to the 3.06 power will give us our answer. So our answer to part B is 21.3 milligrams. That is the mass of carbon-11 present in the sample after 75.0 minutes. Now on to part C of this question. In part C, it says a pure sample of carbon-11 with a mass of 182 milligrams undergoes nuclear decay. Calculate the time in minutes for the mass of carbon-11 to decrease to a value of 36 milligrams. So we know that the initial amount was 182 milligrams. The final amount is 36 milligrams. The rate constant is the same rate constant from part A, 0.0341 inverse minutes, and the time is unknown. That's what we're trying to find. So we'll go ahead and do this math, and we'll solve for T. And T is equal to 1.62 divided by 0.0341 inverse minutes. So our answer is 47.5, and the units are minutes. This is question 6. It says the following three-step mechanism has been proposed for the reaction between Cl2 and C5H10. Part A. Based on this proposed mechanism, write the balanced equation for the reaction between Cl2 and C5H10. So I'm going to add step 1 and step 2 and step 3 together and cross off any substances that appear on both sides of the equation. So in step 1, I see 2 atoms of chlorine, and I see an atom of chlorine as a reactant in step 2 and also in step 3. So I've crossed those off. I see C5H9 as a product in step 2 and C5H9 as a reactant in step 3. I can't cross off anything else, so what remains are my reactants and my products. And so when I add these three reactions together, I get Cl2 plus C5H10, and it produces HCl plus C5H9Cl. Part B, write the rate law that is derived from this proposed mechanism. So I'm going to focus on the slow rate determining step, and in this case that would be step 1. And since step 1 has only a single molecule of Cl2 as a reactant and nothing else, then the rate law would equal rate equals K, the rate constant, times Cl2 raised to the first power. So this is first order with respect to Cl2 because there is only one Cl2 molecule featured as a reactant in the slow rate determining step. In question 7, it says the elementary reaction that occurs between AX2Z and BX is represented by the particle diagram shown above. In part A, it says during this reaction a bond is broken between, so if I compare the molecule AX2Z on the left with the molecule AX2 on the right, I can tell that a bond is broken right here between atoms A and Z. Part B, during this reaction, a bond is formed between, and if I compare the molecule BX on the left with the molecule ZBX on the right, I can tell that a bond is formed right here between atoms Z and B. Part C, the diagrams below represent collisions between reactant particles. Select the diagram that is most likely to result in the formation of the products in this elementary reaction. Assume that each collision occurs with sufficient energy to overcome the activation energy associated with this reaction. So this is focusing on the proper orientation and alignment of the atoms when that collision occurs. Because a new bond is formed between atoms Z and B, the only collision that would allow that new bond to form is this one here in the lower right corner. So that is the correct answer. The proper bond can be formed between atoms Z and B in that collision. Now let's take a look at question 8. It says the conversion of X2 into X is represented by the equation above. It is observed that this reaction proceeds at a very slow rate at a temperature of 20 degrees Celsius. The reaction rate increases at a temperature of 50 degrees Celsius. The graph below shows a distribution for the collision energies of reactant molecules at 20 degrees Celsius. Draw a second curve on the graph that shows the distribution for the collision energies of reactant molecules at 50 degrees Celsius. Now, to remind you, we've seen this in an earlier video. In terms of the collision model, we have the Maxwell-Boltzmann distribution curve, and as the temperature is increased, the curve becomes broader and flatter. And the region underneath the curve to the right of the activation energy in this diagram, that area under the curve increases, indicating that at a higher temperature, a greater fraction or a greater percentage of those collisions have enough energy to overcome the activation energy barrier. So what I'm looking for in the curve at 50 degrees Celsius is that it should be more broad and flat, and the peak of this curve at the higher temperature should be below and to the right of the peak at the lower temperature. So this is one way that you might draw this curve, and the peak of this curve at 50 degrees Celsius should be below and to the right of the peak of the curve at 20 degrees Celsius. So again, the curve gets more broad and flat, and the average energy increases. Now, as far as that region to the right of the activation energy, the curve at 50 degrees Celsius should be above the curve at 20 degrees Celsius, which shows that a greater fraction of the particles at 50 degrees Celsius have the required activation energy needed to overcome the activation energy barrier. All right, let's move on to question 9. In question 9, we are given a diagram that shows two straight lines, and they're labeled as trial 1 and trial 2. Also, we can take a look at the labels on the y-axis and on the x-axis. On the y-axis, it says natural log of concentration of a substance that is listed as X2Y2. X2Y2 is the reactant in this given chemical equation. And on the x-axis, it says time in minutes. So in number 9, it says the diagram above represents data from an experiment involving the chemical reaction represented by the following equation, where X2Y2 is a reactant, and the products are X2Y and Y2. The concentration of this reactant, X2Y2, was monitored over time during the reaction. The graph shown above illustrates the relationship between the natural log of the concentration of this reactant, X2Y2, and the reaction time in minutes. Part A. Write a rate law for this reaction that is consistent with the information presented in the graph. So for this rate law, we've got to figure out whether it's zero order, first order, or second order. Now we do have a straight line, but let's focus on the label on the y-axis. In general, when you have a reaction where you go from A reactant to B product, if the concentration of A versus time is a straight line, then that indicates it's zero order with respect to A. If the natural log of the concentration versus time is a straight line, then it's first order with respect to A. And if the reciprocal, or 1 over the concentration of A versus time, gives you a straight line, then it's second order with respect to A. So here we see that natural log of concentration versus time is linear, so it's first order with respect to this reactant. The reactant is X2Y2, so the rate law is rate equals K, the rate constant, times the concentration of the reactant raised to the first power because it's first order kinetics. In part B, it asks, what are the units of the rate constant K in the rate law that you wrote in part A? Remember that you can have a rate law with a variety of different orders, 0, 1, 2, and 3, and the units of the rate constant are variable depending on the overall order in the rate law. So when you have first order rate law, the units of K in a first order rate law are always inverse time, such as inverse seconds or inverse minutes, etc. So because we have minutes on the x-axis, that means that the units of this first order rate constant are going to be inverse minutes. In part C, it says the initial reaction conditions for trial 1 and trial 2 are different. Identify the variable that was changed in trial 2 that best explains the difference in the appearance of the data in the graph for trials 1 and 2. Now, two common variables that are often changed when you're trying to adjust the conditions for a chemical reaction are temperature and concentration. Now, you can also change other things like the surface area of a reactant, or you can add a catalyst, but let's focus on temperature and concentration for a moment. If we look at these two straight lines, we notice that they are parallel to each other, so they have the same slope. When you plot a straight line to figure out the order with respect to this reactant, if the slope of that straight line is analyzed, it's going to equal the rate constant k. So for the slope of this line, if that's the rate constant k, and we have two lines with the same slope, that means that each of these trials has the same rate constant. Normally, the rate constant will change when you change the temperature. So since these two lines have the same rate constant because they have the same slope, that means they were carried out at the same temperature. So the answer to part C is that it's not temperature. They did not change the temperature. But let's focus on the y-axis. These two red dots that I've placed on this graph indicate that you're starting at a different point, a different y-intercept at time equals 0. And since we're plotting the natural log of the concentration on the y-axis, that means that it's the actual concentration of the reactant. The initial concentration of the reactant in trial 1 was different than the initial concentration of the reactant in trial 2. So the answer to part C is that it was concentration, the initial concentration of the reactant. That was the variable that is different on the graph for trials 1 and 2. All right, moving on to part D. A third trial was performed for this same reaction, in which the initial concentration of X2Y2, which is the reactant, was the same value as what was used in trial 2. The initial temperature of the reaction in trial 3 was lower than the initial temperature in trial 2. So what I'm going to do is put a dot on the graph indicating that where trial 3 should start is at that same y-intercept, because the initial concentration values were the same. But for temperature, remember that temperature does affect the rate constant, so we're going to have a different slope. So how will that slope be different? On this slide, I'm reminding you of something that I had mentioned in an earlier video coming from the Arrhenius equation, and this is the relationship between temperature and the rate constant K. Higher temperature, higher magnitude of K, lower temperature, lower magnitude of K. And because trial 3 was performed at a lower temperature than trial 2, we need a lower value of K, which means the slope of that line in trial 3 should be less than the slope of the line in trial 2. So there are two features of this line that you would be drawing for trial 3. There's two features I'm looking for. The first feature is that the y-intercept of the line for trial 3 should be the same as the y-intercept of the line for trial 2. The next feature is the slope. The slope of the line for trial 3 should be less than the slope of the line for trial 2, because a smaller slope indicates a smaller value for the rate constant K, and this was carried out at a lower temperature, so that is going to be a lower value for the rate constant. All right, now moving on to the final question in this particular packet. This is question 10. So earlier in this video, I had mentioned that even though this summative assessment practice is designed to test the chemistry in Unit 5, kinetics, every so often you may see a part of a question that deals with chemistry from earlier units that you've already studied. So here's an example. Part A of question 10 has to do with a topic, Lewis diagrams, which was topic 2.5 back in Unit 2. So here we go. In the box shown above, draw the correct Lewis electron dot diagram for the C2H4 molecule in which each carbon atom obeys the octet rule. Show all bonding and non-bonding valence electrons. Well, the first thing to do is to count the total number of valence electrons for this molecule. So carbon has 4 valence electrons, and hydrogen has 1 valence electron. So 4 times 2 plus 1 times 4 is 12 valence electrons total. Then I'm going to connect all of the atoms with single bonds to start. So after making those connections, we have every dash counts as 2 electrons, 2, 4, 6, 8, 10. Now I only have 2 more electrons remaining, and if I put that last pair of electrons as a lone pair on the carbon on the left, then the carbon on the right does not have a complete octet, and if I switch it over, then the carbon on the left does not have a complete octet. So I'm going to put that last pair of electrons as a double bond so that each of the carbon atoms obeys the octet rule. All right, let's move on to part B. In part B, it says that C2H4 reacts with HCl to produce C2H5Cl as represented by the following equation. This reaction is carried out in a rigid reaction vessel. Do you predict that the total pressure in the reaction vessel should decrease, increase, or remain the same as the reaction proceeds under conditions of constant temperature? Justify your answer in terms of a description of the gas particles. So here in part B, we have another example where it's not about kinetics or unit 5, but rather the chemistry from an earlier unit that you've already studied. This would be from topic 3.4, the ideal gas law. So we have to think about the relationship between variables such as pressure, volume, temperature, and number of moles. Now we know in this particular problem that it says it was carried out in a rigid reaction vessel. So volume is not changing. It says under conditions of constant temperature. So temperature is not changing. So the two variables to consider are the number of moles and the pressure. What I'm going to do is show you a particle diagram of what it might look like before and after the reaction. I'm just going to draw some particles of C2H4 and HCl as reactants, and then when that reaction proceeds, you would form particles of C2H5Cl. Now, if you count the total number of particles before and after the reaction, you can see I have 8 particles of reactant in my box on the left, and I have 4 particles of product in my box on the right. And these are all gases. So the total number of gaseous particles is going to decrease as this reaction proceeds because we have a total of 2 moles of gas in the equation on the left, and we have 1 mole of gas in the equation on the right. So the answer is decrease. The total pressure in the reaction vessel should decrease, and it's about how the number of gaseous particles in the reaction vessel is decreasing as the reaction proceeds over time. Now, as you will see, the remainder of this question does relate to Unit 5, kinetics. Let's take a look. It is proposed that the formation of C2H5Cl from C2H4 and HCl proceeds via the following 2-step reaction mechanism. Part C, write the rate law that is derived from this proposed mechanism. So remember, when you're given a mechanism and you have to come up with the rate law that is derived from that mechanism, you focus on the slow rate determining step, which in this example would be step 1. All we have to do is focus on the reactants in step 1, and I see 1 molecule of C2H4 and 1 molecule of HCl featured as reactants. So therefore it's first order with respect to C2H4 and first order with respect to HCl. So here comes our rate law, which is rate equals K, the rate constant, times the concentration of C2H4 to the first power, times the concentration of HCl, also to the first power. And that's it. 1 molecule of each as reactants in the slow rate determining step. So it's first order with respect to each reactant. Part D, a student makes the claim that the ion C2H5 plus behaves as an intermediate in the proposed mechanism shown above. Do you agree or disagree with the student's claim? Justify your answer. Remember that a catalyst, which is different than an intermediate, a catalyst would be added at the beginning of the reaction as a reactant and then eventually produced as a product in a later step of the mechanism. But what we have here is in fact an intermediate. C2H5 plus is formed as a product in step 1, and then it is consumed as a reactant in step 2. So yes, I would agree with the student's claim because the substance C2H5 plus behaves as an intermediate. It is formed as a product in step 1 and consumed as a reactant in step 2. That is the definition of an intermediate. All right, the next part of this question involves an energy diagram. It is determined that the overall chemical reaction is classified as exothermic. So where should the products be relative to the reactants in terms of energy? Well, if it were endothermic, then the energy of the products would be higher than that of the reactants. But because this is exothermic, the energy of the products should be lower than the energy of the reactants. And then also we have a two-step mechanism. And in the two-step mechanism, step 1 is slow, so it should have the larger activation energy. Step 2 is fast, so it should have the smaller activation energy. So if you're going to think of it as a hill, you should have a taller hill to climb for step 1 and a smaller hill to climb for step 2. The last part of this question says, on the energy diagram that you drew above, draw a vertical arrow to indicate the magnitude of the activation energy barrier for the rate determining step. That's going to be the slow step, which is step 1. And we go from the energy level of the reactants to the top of the hill. So that arrow indicates the activation energy of that slow rate determining step in the mechanism. Well, that particular part, part F of question 10, is the last part of the question. So this is the end of the video. I hope that you found these answers and explanations helpful. Thanks for watching and good luck studying for your Unit 5 summative assessment.